Greetings and salutations, my name is Little John, and welcome to an introduction to finite state machines, also known as FSMs. So, as you know, you have a finite state machine is basically a diagram. It's a picture that shows going from one state to a next, where each state has some sort of output and is determined how you get there by some sort of input. But in general, so the states themselves are depicted by these circles, and within the circles you have the state name or description, such as going from floor 1 to floor 2 or floor 3 if you're trying to design a finite state machine that describes the process of an elevator. Or what if you're trying to design the process or the finite state machine that helps you determine a traffic light. So you would have several traffic lights, left turn lane, right turn lane, etc., so on and so forth. So you would describe each one based on what you want that state to do. And that's typically what is written on the inside of the circle. So another thing to note is your initial state, where you start from when the entire system is booted up, is depicted by an arrow coming into the state from nowhere. And that'll make sense as we go through an example that shows you how that happens. Also, the number of states you have determine the bit width of the state definitions in binary. So if you have approximately 4 states, which in binary you could describe from 0 to 3, since we typically count 0 as a number. So from 0 to 3, we can use 2 bits to describe a state. And this will all make sense as we go through the examples. A subnote of that, though, is that you have your states and you have your next states. Your next states are legitimately just your current state, where you're going to go. If you're in a current state, your next state is where you're going to go based on what happens in your input. Again, this will make sense as we go through the example I have set up for you guys. Also, a typical assumption that all finite state machines have, unless otherwise stated, is that each transition happens on the rising edge of your clock signal. Just an assumption that is not really said a whole lot, so just wanted to put that out there. So unless it's otherwise stated, you can assume that each transition, so each state change, happens on the rising edge of a clock, which means that once you boot up and you start at your initial state, your state machine will continuously go until, there's no more clock signal or no more power, etc., etc. Anyways, just wanted to throw that out there. So here's the example I have for you guys. Draw a state diagram for an FSM that has an input X and an output Y. So it's very simple, one input, one output. Whenever X changes from 0 to 1, Y should become 1 for 2 clock cycles and then return to 0, even if X is still 1. So based on this, I know I need my initial state. When everything is 0, I need my initial state where X is 0 and my Y is 0. And then I need 2 states, one after the other, because of that whole rising edge transition signal. I'm going to need 2 states where Y is 1, one after the other. And that means I'm going to have a total of 3 states. But let's go ahead and define a 4th state, just in case we need it. That's going to make a little more sense as we go through. But we may need a 4th state. And it'll make sense as we go through. So we're going to go ahead and say we're going to need 4 states. We may only need 3, but we're going to go ahead and say we need 4. So now we need to start defining our states in binary. Now, as I said, our initial state, where we start from, is where everything is 0. So it makes sense that our initial state is going to be 0, 0. Since we're using 4 states, or we're defining 4 states at least, we're defining 4 states. We want our first state, our initial state, to be 0, 0, because that's where everything starts at 0. Everything is initialized. So yeah, 0, 0. Also, I have here S is defined as S sub 1, S sub 0. This is going to help us when we look at our truth table that we're going to set up, the way you set up these truth tables for these FSMs. So, because there's no real description on each state, we're just going to give them letters. Because really, we don't have a very descriptive example here, like a traffic light or an elevator. So we're just going to give them letters. And again, this is also just because we want a simple example to go through. So we define them in order logically. A is 0, B is 1, C is 2, and our last state, D, is going to be 3. In binary, not in decimal, just to clarify. Anyways, so to make this a little bit easier for you guys, what I did is I set up our current and next state with the letter definitions that we used versus the binary definitions that we used. And this is just to help you get used to how you set things up and how everything works. So, based on our definition, our initial state, which is our current state going from top to bottom, A, our initial state, if X is 0, we're going to stay in A. Because it's only when it transitions from 0 to 1, our X value, that we want to start that process of going and putting Y to 1 for 2 clock cycles. So, which means that if our current state is A and our X value becomes 1, our next state is going to be B. Now, our output for Y is based on that current state that we're in. Just, especially for this example. So, just giving you guys a heads up on that. So, as you can see in our truth table, if our current state is B, no matter what our X value is, if it's 0 or 1, we will still go to C, which helps us take care of that. Our Y value must be 1 for 2 clock cycles. Now, if you look at the truth table, when current state is C or D, it matches our current state C when X is 0. That output matches our current state D when X is 0. So maybe we really only need 3 states after all, based on the way this truth table looks. Now, we can already see something's a little off based on those outputs. Not based on the next state, but based on Y. But let's go ahead. We'll draw it, our FSM, our state diagram. We'll draw that with 3 states, and I'll walk you through more or less what's going on and why we may want to keep that 4th state, that D state. So here you can see that we have a different truth table. This is the actual truth table you're typically going to see. You're going to see the binary definitions of your states, not the name. So, again, this is S sub 1 and S sub 0. So if our initial state is 0, 0, our A state, when x is 0, our next state is the A state. So you see that n sub 1 is 0 and n sub 0 is 0. Now if our initial state is 0, 0, A, and x becomes 1, we know, based on our definition, we know that we're going to go to B. So if you look, n sub 1 is 0, and n sub 0 is 1. So hopefully that previous truth table that I showed you guys will help you understand why we do things the way we do. And this will help you understand the differences for those bits and the next state bit, each subscript for the S1 and N1, they're all related to each other. Next state is still using the same definitions that we defined for the states. That's the key. So hopefully this helps you and makes a little bit more sense. So now we're going to go ahead and start drawing our FSM. So we start out with our initial state, which we defined as A. In that initial state, y is 0. And as you can see, there's an arrow coming in from nowhere, which means that it is our initial state. So that part is taken care of. Now let's move a step forward. So, if our x value is 0, we're going to stay in our initial state because nothing happens. We want it to stay 0. It's only when x becomes 1, so we have our x, that we go and we start the process of y being 1 for 2 clock cycles. So we go to B, and then we go to C. Now you can see here that there's no x values next to the arrow going from B to C, which means that it's not dependent on the input. It will definitely go from B to C. Once you go to B, you will most definitely go to C on the next clock cycle. So that means we've taken care of the requirement that y be 1 for 2 clock cycles. Now let's look at that requirement that it goes to 0 even if x is still 1. So let's look at this the way it is. So we don't have an x next to the arrow going from C to A to show that we don't care what x is, even if x is still 1. So if it's 0 or 1, we want y to go back to 0. Which, if x was 0, then it's fine, and it goes back through the cycle when x goes 1 again. But if you think about it carefully, if x was 1 when you're in C and you're going to A, that means that y will go to 0, but it'll go right back to 1 again. It'll keep doing that, and it'll be on this loop for a long time until x goes to 0. And then you'll stay in A. But we don't want that to happen. That's actually a problem. Based on the statement we were given, that's a problem. So let's see what happens with that truth table that we set up where we had the D state as well. So let's see what happens there. So based on the truth tables we developed and on the statement we have, we go to D if x is 1. So even if x is 1, we want y to go to 0. So, but if x is 0, so if we have x naught, then we can go right back to A. It's fine if you're in the C state. But if it's 1, we want it to go to 0, no matter what. So in this case, that means that when x is still 1, you want to stay in that last stage to make sure that y stays 0. Otherwise, you'll have the problem like before where you only had the 3 states and it just loops, which we don't want. It is only when x transitions from 0 to 1 that we want y to have that loop of being 1 for 2 clock cycles. So that's where the key part is. Only when it transitioned from 0 to 1. Not from 1 to 0, when it goes from 0 to 1. And that's what this fourth state helps us take care of. So, hopefully that is a great example and it makes more sense now and you're able to understand how to develop your FSM, how to draw that state diagram and move forward. Anyways, so thank you all so much for watching and I will see you in the next video. TTFN!